Hello everyone, welcome to our differential equation class. In this video we review the main ideas for the exam number 1. Let's start with the settings of the exam. The exam is going to cover basically what we have seen about chapter 1, which is essentially sections 1.2 through 1.6 and also section 1.11 in our textbook. So the exam is 2 hours long. On Thursday opens at 1 p.m. is due at 8 p.m. and is gonna close at 10 p.m. So essentially here we have a graphical representation. It's gonna open at 1 p.m. The exam is gonna open until 10 p.m. This is the time the exam is gonna open, but the exam is due at 8 p.m. So students should start the exam anytime between 1 p.m. and 8. The idea is that if you start anytime in this green zone, then suppose you start the exam is 2 hours long, and suppose you have a problem with internet, and for whatever reason you have to exit the exam. You have to go out of the exam. Then you reboot your computer, and then you can log back in and you can keep working because the exam is open until 10 p.m. So you are safe. If you start before 8 p.m. and for any reason you need to quit the exam, you can go back and continue. The exam is actually, we say is 2 hours, but in fact the math in the exam can be done in 1 hour 30 minutes. And we have 30 extra minutes for any technical issues you may have, or if you don't have technical issues, then you can use this 30 minutes to think about the exam problems. But the exam that we are taking is essentially should be done in 1 hour 30 minutes at the longest. So you have extra 30 minutes for whatever thing can happen. But if you start any time after is due at 8 p.m., suppose you start here at 9 p.m. and the exam is going to be 2 hours long, no problem. So you're going to finish after 10 p.m. and it's fine. But if you have any technical issue after 10 p.m. and for any technical reasons you need to quit the exam, and your exam is still going to be running, but you are not going to be able to get back into the exam after 10 p.m. because the exam is already closed. So essentially your exam is going to end here when the glitch happens. So to avoid that, please start the exam before it's due at 8 p.m. Then the whole exam is going to be in the region where the exam is open, which is this region, and you are safe. You can always log back if you have problems with the exam. So this is the reason we have this type of settings in the exam. The exam is online in D2L. You take it with the lockdown browser. The exam has 10 problems. 7 are going to be multiple choice, 6 points each, and this is more or less 40% of the exam. 3 questions are going to be what they are called written response. You write on paper and then you upload your work and the TA is going to grade it, and this is essentially 60%. Total 100 points. The exam has a formula sheet included. The same formula sheet you have for quizzes is included in all tests in our class. No paper copies are allowed. You just need to scroll down and you're going to see the formula sheet inside the exam. And whatever problem you're working, scroll down, you have the formula sheet. You can use the allowed calculator that we mentioned in D2L, but that's all. No phones, no notes, no review sheets, just the allowed calculator. That's all you can have. There is a practice exam 1 online in D2L. Take it when you think you feel ready to take the exam. The multiple choice part, if you take it, it counts for extra credit, but don't think about the extra credit. Try to do the exam just to see how much you know, what are the weak points in your preparation. But if you do it, you have the extra benefit of extra credit. There are some practice problems also online in the homepage of our D2L class, some PDF file with some practice problem. These are the settings for our exam, and now we can move on to the actual review part of this video. So the next part of the review is to go over some exam problems that they have more or less the same difficulty as the problems in the exam. So here they are more or less. So what we are going to do in this review is we are going to try to solve this equation. It's an equation you should be able to solve if you have done the homework and go to class. Then we are going to have a qualitative graphs of solution of this equation. We are going to try to identify which is the differential equation that corresponds to this slope field. We are going to work a little bit with the logistic equation, and we need to answer this question that we are going to go in a minute. Then solve one more equation, and then use the approximation method we have studied in section 111 to solve this equation that otherwise is pretty difficult to solve. So that's the plan for the review today. And you can pause the video and see which question you think you don't have much idea what to work, so and try to solve that question, and then in the video see what is the answer, or in the PDF that I'm gonna post together with the video. Alright, let's go to the first problem. So that is here. We have this equation right here is a differential equation, and now we need to solve it and find the solution that satisfies this initial condition. Okay, solution. How we can do that? So it looks like this is an equation that doesn't look separable, doesn't look linear, so in principle we should not know how to solve it, but maybe with some little algebraic transformations we can rewrite it in a way that we know how to solve it. For example, here is one idea. We have a factor t right here. We have a factor t there, so we can pull it common factor. And here we have factors t and factor t, so 1t can be also pulled common factor in the numerator, like this, t squared plus cosine of t. And in the denominator we can play the same game, and we can pull a t common factor, and then we have 2y plus 5. And of course this t can cancel with that t. Alright, so since we have that, now the equation looks in much nicer form, because now we can realize, the denominator depends only on y. So we can multiply, we can move it to the other side, multiplying by that denominator. So what we do here is we multiply by 2y plus 5, one side of the equation and the other, 2y plus 5, and of course we cancel these two, and then the final result is that this factor goes to the other side. Okay, so let's write it down, and let me write it down like this. This is a function y of t we are trying to find, plus 5, all that is multiplied by y prime of t, and all that is equal what is on the other side, t squared plus cosine of 2t. Alright, this is what we got, and now we see very clearly that this equation is actually separable. You see, separable. Here we have the part that depends on y, this is the part that depends on t, and the part that depends on y is multiplied by y prime. Perfect. So what we can do now, because it's separable, is just integrate on both sides with respect to the t variable. And because it's separable, then we have guaranteed that this can be changed, these functions can be changed into the new integration variable, and this is the y. And then what we have here is 2, but now is the variable of integration y plus 5 dy, and on the other side we have what we had, which is t squared plus cosine. I put 2t, and I would like to see why. I have a 2t here and a 1t there and a 1t, so this 2t is a mistake. That is always good to double check what we are writing, so just we don't create things that they shouldn't be from one step to the other. Here is t, and we only multiply by that, so that should still be t here. So cosine of t dt, perfect. So now we integrate on both sides because these are simple integrals, and what we get here is 2 y squared over 2 plus 5y plus a constant here, plus a constant. But we are going to have another constant here, so different constants, c1, c2. So I'm going to put these two constants together. And then I'm going to say here is t cubed over 3. So now we need to integrate the cosine, and which function the derivative is the cosine? Well, that function is the sine of t. And then the integration on both integration constants together, and let's call it c0 there. And of course we can simplify these two terms from here, and that is a nice implicit form of the solution. We have solved the differential equation, and this is an implicit solution. Okay, so this is an implicit solution, and actually we can find the actual solution by writing the initial condition right here in this equation. So we are going to do it this way, and then we are going to do it a different way, but right now we can find out which is the solution of the initial value problem by saying what this condition means. This condition here means, how do we put this condition into the implicit form of the solution? We need to realize that this condition means that when t is equal 0, y is equal 1. And that is what we need to put into the implicit form. So we replace initial condition, we replace y by 1, so 1 squared plus 5 times 1, and we replace t by 0, so 0 plus 0 plus c0, and from here we get that c0 has to be 6. So this is the simplest way to find the integration constant. And now the implicit form of the solution is y squared of t plus 5y of t is equal t cubed over 3 plus sine of t plus 6. Okay, that is our solution. If the problem doesn't say anything, we can leave it like that. If the problem says find the explicit solution, let's put it explicit. Well, then we need to work a little bit more, because this is the implicit solution. This is implicit. Implicit means we have an algebraic equation for our function. Y squared plus 5y is equal all this. How we solve for y when we have a quadratic equation like this equation here? Well, let's put this term on the other side with the opposite sign. So we have y squared plus 5y, and then we have minus the whole thing here, t cubed over 3 plus sine of t plus 6, all with a minus sign in front, equals 0. Notice that this equation is an equation of the form a times y squared plus b times y plus some c coefficient that in this case depends on time, but is still a coefficient that doesn't depend on y, equals 0. So this is essentially what to find for y. What we need to do is find the root of this quadratic equation in y. And we have a formula for the solutions. The formula for the solution is that we have two solutions, y plus minus, and these solutions are going to be 1 over 2a, and then here minus b, plus minus the square root of b squared minus 4ac. And in this case, c is a function of t, but it doesn't matter. The formula works perfectly fine with that. So that is how we find our, and notice we are going to get two solutions, and we are going to need one more page. We are going to get two solutions, but the solution has to be unique. We are going to talk about that in a minute. All right. So what are our two solutions, y of t? Well, notice that in our problem, from here we see that a is equal 1, b is equal 5, and c of t is that whole thing with a negative sign. Negative t cubed over 3 plus sine of t running out of space plus 6, all under the negative sign. Okay, so that is what we need to put there. If we do that, we are going to have a is equal 1, we said, so 1/2. B is 5, so minus 5 plus minus square root of 25. So far is simple. And now minus 4, a is 1, and c. And c is negative 1, and then we have the coefficient c, which is t cubed over 3 plus sine of t plus 6. All right, and then we compute the square root, and everything multiplied by 1/2. So there we have it, and now we have two solutions, the y plus and the y minus. Let's rewrite this a little bit better, but not much, because there's not much we can do about it. So 1/2, let's put negative 5 plus, let's write it separately, both of them. The solution plus is going to be with the plus here, and it's going to be square root of 25. We have here minus minus, so these are going to cancel out, so we're going to have plus 4, and well, all that thing, cube over 3 plus sine of t plus 6. Cool. And the other solution is going to be essentially the same. Copy, paste here, but is with a minus sign. So it's going to be the solution minus with a minus here. So now, which one of the two solutions is the solution of our problem? Because we have apparently two solutions. We already fixed the constant c, which is 6 here. So we have two solutions? Actually, no, we have only one. Because when we compute the square root, we have two possibilities here, but only one is solution of the differential equation. And the reason is, let's go back to the initial condition. We already used the initial condition, but we need to use it again. Y at 0, we said, is 1. What happens when we put y plus at 0? Y plus at 0 is 1/2 negative 5 plus, and then we put 0, so this is going to be 0, this is going to be 0, all this is going to disappear, and we're going to have 24 plus 25. So square root of 25 plus 24. I should have done this calculation down here where I have more space. Okay. What is that? That is 1/2 minus 5, and then here plus the square root of 9 and 4, which is 7. So we end up with y plus of 0 equal 1/2 negative 5 plus 7, which is 1. So this y plus satisfies the initial condition. Perfect. Look what happens with the other solution. The solution minus at 0. The solution minus at 0 is 1/2 negative 5 minus this whole square root of 25 plus 4 times 0 plus 0 plus 6. Like this. So it's going to be negative, obviously, because we have two negative terms. 1/2 minus 5 minus square root of course, 49 again. And this is 7. So let's put it here. 1/2 minus 5 minus 7. So we have 10, 12. So this is negative 6. So this second equation, the second solution we found, that does not satisfy the initial condition. And then we have only one. And the only equation that satisfies the initial condition is this one. So a little bit of algebra at the end. So the differential equation part was easy to compute. The problem here was to compute the explicit solution, which we needed to use a lot of algebra. But here it is. This is the solution of our differential equation. Our next problem is to find a qualitative graph of solutions to this differential equation. And we can do it. Solution. Oops. In this way. We are going to write the differential equation y prime as a function of y, where of course the function of y is the right hand side in the equation, y plus 1, y minus 1. Okay, what do we do now? The first step is always in this type of problem, find equilibrium solutions. Equilibrium solutions. Which are equilibrium solutions? These are the constants solution of the differential equation. So you put a constant here, constant. Because it's a constant, this is going to be 0. And then you need to solve the equation f of y equals 0, which is y plus 1, y minus 1. Then obviously these equilibrium solutions are going to be each of these factors equals 0, so y equals 0, or y equal negative 1, or y equal positive 1. And these are our equilibrium solutions. Okay, and now what do we need to do? We need to find the intervals of increasing, decreasing for all possible solutions. So 2, increasing, decreasing. Intervals. Alright, so how do we do that? Well, we have clearly intervals defined by this equilibrium solution. So let's go to the right of this equilibrium solution, y equal 1. So let's start saying what happens when y is bigger than 1. We are on the left of the largest equilibrium solution. Okay, in that case, f of y, recall f of y is y plus 1, y minus 1. But because y is bigger than 1, then this factor is positive, and of course all these other two are also positive. So this is positive, this is positive, and this is positive. So we have a product of 3 positive numbers, so of course this is positive. Which means that the derivative of the solution is positive, therefore the solution itself has to be increasing. And we denote it like that, with an arrow pointing upwards. What is the next relevant interval? Well, y y less than 1 but bigger than 0. That is the next interval. And now let me copy all this again. Copy. Let's put it here, paste. And what do we do? What do we have here? So now we are y less than 1. Because y is less than 1, this factor here is negative. So this is negative. But because y is bigger than 0, then this is positive, and of course this is positive. So positive, positive. So this whole thing, this product, is then negative. And that implies the solution have to be decreasing. Running out of space here. So let's move it a little bit downwards. Now, what happens with the next relevant interval? The next relevant interval is when we are above -1 but bigger than 0. So, what happens when we have y is actually above -1 but smaller than 0? So, what happens there? So, recall we have our function here, and our function then is going to have, this is negative, so of course this is negative and this is negative. We just said that, so negative and negative, but we are above -1, so this is positive. Alright, so now we have 2 negatives and 1 positive, so the whole thing is now positive, because negative is positive. And then y, the solutions are increasing. And the last interval we need to consider is what happens when y is super negative, less than -1. Well, in that case, again, we have our function f, and now everything is going to be negative. This factor is going to be negative, this factor is going to be negative, and now this factor is going to be negative, so we have 3 negatives, so it's actually negative. So the solution is decreasing. And there is what we wanted to find. So now we picture all this. So let's move this a little bit. Oops. So what I am doing, I'm doing something not right there. That's what I wanted to do. So let's go here. So the first thing we need to do is we need to put the equilibrium solutions. Here is one. Let's suppose the other is here and the other is here. Notice what we are doing here. We are graphing y prime versus y, or what is the same, f of y versus y. And we said, and here we have a 1, then we have 0, and then we have -1 over here. And we said bigger than 1 over here, the function is positive, and when we go to positive infinity, everything goes to infinity. So and then we are alternating signs. So the graph has to be something like this, something like this, something like this. I can do a better graph later, but essentially that is how the graph looks like. And now we have the interval of increasing, decreasing. Here is increasing, here is decreasing, what we were saying right there. And then we have increasing again and decreasing again. And now we grab the information on this axis, which is the y-axis. We put it in the vertical axis. You see, here is the solutions, the information, and we put t on the other axis, and we start plotting things. For example, the equilibrium solutions. They don't depend on time. So we are gonna have, we are gonna have 0 here. So constant, I mean -1. Constant here. And constant here is gonna be hard to see, but let me put it like this. Constant. These are our equilibrium solutions, 0, 1, -1. Now here we see that the solutions have to be increasing, so that means the solutions with these initial conditions, they have to go something like this. They cannot cross, isn't it? What happens with the solution here? Well, they are decreasing, but they cannot cross the equilibrium solution, so they have to be something like this, and here maybe something like this. And now here the solutions are increasing, but again they cannot cross, so maybe something like this, and here something like this, and then here the solutions are decreasing. And that is how the qualitative graph of these solutions can be constructed, by doing a little analysis on the right hand side of the differential equation. In our next problem, we need to identify which is the differential equation among these possibilities that produces this slope field. Alright, solution. What we can do here. So, suppose the answer for, we write the answer as answer is an equation of the form y prime equal f of dy. Suppose we write the answer in that form. The first thing we notice in the is not going to help us much here, but the first thing we notice in this slope field is if we move on the horizontal axis, the t-axis, nothing changes. Everything is the same when we move in the horizontal axis. And for any value of y, take this value, the slopes are always the same along the horizontal axis time. And that means, so the graph says, or the slope field in the picture implies that the function f, which we wrote it as the most general function of t and y, actually does not depend on t. It's just a function of y, which is nice to know, but in this problem is not going to help much because all the options here don't depend on time. But if you have an option that has t here, t squared, then you cross it out immediately because it cannot, there is no t dependence here. Okay. So what other things we see from the graph? Immediately we see that the slopes here are horizontal and the slope here are horizontal. So let's write this down, the horizontal slope here and horizontal slopes there, which means the other thing that the slope field is telling us is that f at 0 is 0 and f at 2 is 0. That could be important information, but in all the options we have, actually that happens. Y at 2 here is 0, this is satisfied, all these are satisfied, and at 0 they are also satisfied, so this is not much help, but it's good to know. It could be help in other problems, but not in this. But now we need to start looking at the signs more or less like we did here, and on the different intervals. We need to do a similar analysis here. For example, notice that over here the slopes are positive. This is positive slope when the slope have this form. So what we know that if f of y, so f of y is positive for y bigger than 2. Okay, bigger than 2, f has to be positive because this is what we see here in the picture. But now notice notice b and if I did it correctly, and c. What happens with b and c? Well, when y is bigger than 2, this is negative, and this is positive, and this is negative, so the whole thing is negative and it has to be positive, so that eliminates b. And the same with c, eliminates c because of this factor. So let's put it down here. This condition implies it cannot be either C or B. Alright, so the sign here eliminates two options. What happens with the sign down here? Well, the sign here is negative in that interval. Okay, what is that? So let's write that down. F of y is negative for y in a particular interval less than 2, bigger than 0. What that implies? Well, let's take a look. So let's erase these two. So what happens, for example, in the first option? Let's put it here. The first option. We are less than 2, so this is negative. So this is negative. And bigger than 0, so this is positive. So this is negative. A is negative. Okay, satisfy that. So that's okay. We cannot discard that option. What about here? We already discarded these two, so we don't look at those anymore. So here we are between 2 and 0. Well, between 2 and 0, but between 2 and 0, this is negative, and 0, this is positive, so negative. Okay, so D satisfies that. What about E? Notice the square here. Y is less than 2, so this inside the square is negative, but because of the square becomes positive, and because it's bigger than 0, this is positive. So there it is. This whole equation E is positive in this interval, and we want it to be negative, so that cannot be. Things we square here, and the same for the next one. So these options eliminate E and F. E and F both have to go. And now we have only two options, A or D. And that is going to be decided probably by the sign here. For y less than 0, it has to be negative. So y, f of y has to be negative again. So negative again. So it was negative here, and now it has to be negative again. So it goes to 0 and then back to negative. Okay, and this is for y less than 0. Okay, what happens here? And we have only two options, A and D. Okay, so what happened with A? Recall, negative. So because it's negative, that means this is negative, and because this is negative, so the product of negative is positive. Oh, that's wrong, because it should be negative, so cannot be A. So cannot be A. Let's hope it's D. This should be negative. If it is negative, that is our solution. So recall, less than 0, so this is negative, and we have a square here, so it's positive. So negative, positive, negative. Perfect. So our option is actually D. And all this implies then that the whole thing implies the option is D. This is more or less how we solve this type of problems. In our next problem, we have logistic equation, and the question says consider this initial value problem. So we have the logistic equation with a hunting or harvesting term and some initial condition, and what we need to do is to find out whether the population solution of this equation with this initial condition, that population survives or goes extinct. Okay, so one possibility to solve this equation exactly, which we didn't do in class or in the videos, and figure it out, or understand the behavior of the solutions in this picture, and then based on that answer the question. So, and this is what we are going to do. we are going to go on with the qualitative method. So, solution. How we find a qualitative graph of solutions to this equation for many initial conditions, and later on we put that, but for many initial conditions. What happens with the solution here? Well, there are important points to graph. For example, suppose we don't have harvesting, then the equilibrium solutions are 0 and 100. So these are important points that we should plot here. The 0 is not an equilibrium solution of the whole equation with harvesting. 0 is an equilibrium solution when we don't have harvesting, which is not our case, but it's an important point. Let's put it there. And the other is, let's put it up here, is 100, which is essentially what we call in other videos K, and this is the carrying capacity. Carrying capacity, which is essentially the population that can be sustained by the finite amount of resources available when we have a population described by this logistic equation. Okay, these are two important points. What else? We have 1, 2, 3, so 1, 2, 3, 4. So more or less here we have the middle, isn't it? Okay, so let me put the middle more or less over here, so that should be 50. It's a good thing to know where the middle is. Okay, these are the 2 points, but we haven't learned anything about the solutions of the differential equation yet. But these are points, they are going to be useful later. What do we do here? Well, we start exactly doing the same thing we started in the previous problem. Find equilibrium solutions. Equilibrium solutions. All right. What are the equilibrium solutions here? They are constants, solution of the equation. So because they are constants, this is 0. And on the other side, we have 5p, 1 minus p100, and then minus 100. All that equals 0. So we need to find the roots of a polynomial. And what polynomial it is? Well, we distribute, we rearrange terms, and we are going to have negative 1 over 20, I did a simplification there, p squared plus 5p minus 100 equals 0. Okay. Before trying to compute the roots of this parabola with the formula we have used earlier, it's a good idea to get rid of these fractions by multiplying everything by negative 20. Calculations are going to be easier if we don't have fractions in it. So if we do that, so you see what happens. We multiply everything by negative 20. So the negative 20 goes here, goes there, and goes there. When it goes here, it cancels out. And here we are going to have 5 by negative 20, so we are going to have negative 100. And here we are going to have a positive, well, p, positive 2000. All right, so let's do that. And then we are going to have p squared minus, what did we say we are, doing? Multiplying by 20. So negative 100 times p positive 2000 equals 0. So now we use the formula for the roots, and we are going to have two roots, p plus minus, that they are going to be 1/2. Then we are going to have 100 plus and minus the square root of 100 squared, so 10,000. 10,000, this is 100 squared, minus 4 times c, which is 8,000 then. Okay, so we see that we have a couple of big numbers there, but nothing to worry about. 100. So this is plus minus the square root of 2000 again, when we do the difference. And well, we could keep simplifying, but now is a good time to grab a calculator and write this as 1/2 100 plus or minus, and here we're gonna get something like 44.72 if I did it correctly. Okay, good. So we have two solutions. The p plus, when we add up and divide by 2, that is gonna be something like 72 something, 72.36 again if I did it correctly. And the p minus is gonna be when we subtract the two numbers and we divide by 2, so it's gonna be 27 point something, 64, whatever. So now is when we need to remember what we know about this equation. We have found two equilibrium solutions. One equilibrium solution is below 50, the other is above 50. One is, suppose if this is 50, that here is 25, and this is a little bit higher than 25, let's say around here. And this is p minus. And then the other is a little bit below 75. 75 should be here, so a little bit below should be somewhere here. And this is p plus. Now these are equilibrium solutions, so now we know that the solutions here are like this as a function of time. Perfect. And now we need to use what we know about this equation, or we need to rediscover it again. So I'm going to use it, I'm not going to redo it. But recall, this is a parabola, as you can see here, that opens downwards, and we have two roots. So let's do a little picture just to remind us that if we do this picture where we put p here, and we put f over there, and we have the two roots here, the parabola is something like this. So our intervals of increasing, decreasing are decreasing, increasing, decreasing. And recall, this is p minus that we just computed, and this is p plus. So all I'm trying to say here is that we know that the solution down here has to be decreasing. We know the solutions here have to be increasing, and we know the solutions have to be decreasing down there. So we end up with something of the form solutions like this. Again, solutions never cross each other. Solutions like this. Solutions maybe like this. I cross here. It's difficult, but okay, something like this. And then here solutions like this. And we mentioned in a previous video that these solutions have go to zero in a finite time. They cross here 0. So the population go extinct in this region, and we call this region, for that reason, we call this region here the extinction zone. Extinction. So, what is the extinction zone in our case? Extinction zone. Once we know that, well, the extinction zone is from 0 to p minus. To p minus, which is 27.64, blah, blah, blah. That's the extinction zone. Every initial data in that region goes to 0 in finite time. I'm gonna use this. I already don't like it. I'm gonna use the same colors here to denote these intersections. So much nicer now. So okay, is our initial data there or not? So since our initial data p at 0, what was it? 25. Oh, we are doomed. 25. That implies that our initial data is smaller than the smaller root p minus. So p0, our initial data belongs to, this is the symbol, belongs to the extinction zone. And that's it. We solved the problem. We know what is going to happen. Nothing good, but that is what is going to happen. The population goes extinct. Extinct. And that's it. That's how we use what we know to answer this type of questions. Let's move on to the next problem, and the next problem is pretty straightforward. It's a calculation. We have a differential equation. We need to solve it. Solution. Well, what type of equation is this? Doesn't look like we are going to be able to separate the equation because we have t here, t there, and only y here. But notice we have y to power 1. The equation is already in normal form, so this is what we call a linear equation. A linear equation, which, by the way, is not separable. Horrible. It's not separable, so we need to solve it with the integrating factor method. Integrating factor method. This is the only way we know how to solve this equation. And how we solve this equation with the integrating factor method? Well, we grab all the y dependence and we put it on this side to t y. Let's put it here, and we leave the exponential on the other side. And it's a very complicated exponential. And what we do now is we multiply the equation, the whole equation, by the integrating factor, which is going to be a function of t that we don't know yet. But we distribute, and then we end up with mu, which is a function of t. I'm not going to write it again, minus 2t mu multiplied by y, and over here, well, we have mu multiplied by the exponential of t squared plus 2t. All this is in the exponent. And here is the key part then of the integrating factor method. These three factors, including the negative sign, have to be equal mu prime. That is what we want. So let's solve for mu. So the equation for mu is then mu prime has to be equal negative 2t mu in this case. Notice that this equation is separable, and that's the whole point here. So separable. This equation, well, it's not written as separable right now, so I shouldn't point here, but as soon as we divide by mu, like in this equation, is separable. So this equation is separable. And then we know what to do. We can integrate on both sides and solve. If we integrate, we are going to get here the natural log of the absolute value of mu. Over here, we are going to get negative t squared plus a constant c0. And now we compute exponentials on both sides, and we have absolute value of mu equal exponential of negative t squared plus c0, which, by the way, is exponential negative t squared exponential c0. And then mu of t is going to be just c1 exponential negative t squared, where we introduce c1 to be plus or minus exponential c0. It doesn't matter, it's just for reference for us. Okay, that is the functions, the group of functions proportional to this exponential that we need to use to solve this linear equation. So let's use them. We have here c1 exponential negative t squared multiplied by y prime minus 2t exponential c1 exponential negative t squared y, and over here we have c1 again exponential negative t squared times exponential positive t squared times exponential, I'm splitting that exponential, 2t. And see what happens. The first thing we are going to do is get rid of the constant, because the constant is not helping at all. We could also get rid of the exponential, but then we are back where we started, and we don't want that. What we want is to realize, let's write one more step. We have here exponential negative t squared y prime, and notice what do we have here, right here. All this is plus exponential negative t squared prime. Compute the derivative, and you see you get what we have up there, times y. And over here the two exponentials cancel out, and we have only exponential 2t. And on the left side we have a total derivative now, exponential negative t squared times y, this is the derivative here, prime, equal exponential 2t. We integrate on both sides, because we can now. The integral of the derivative cancel out, and we have exponential, exponential negative t squared y plus a constant, but I'm gonna put all the constants together. Here we integrate, so 1/2 exponential 2t plus a constant c1, c2, let's call it c2, doesn't matter. And now we multiply the whole equation by the exponential here. So what we do now is we multiply everything by exponential positive t squared, exponential positive t squared, and we have a cancellation on the left side. And on this side we are going to have c2 exponential, this is an exponential positive t squared plus 1/2 exponential, this e are terrible, and this is not better, exponential t squared plus 2t. So these are all the solutions, and now we need to use the initial condition. What is the initial condition? Y at 0 is equal to -1. So I should have written in a more clever way, -1 is equal y at 0, and we have y at 0 is c2 plus 1/2. 0 here is 1, 0 here is exponential of 0 is 1. So what I use here is that, of course, exponential 0 is 1. And there it is. C2 is -3/2. Once we have that, we have the solution. Y of t is equal, we can pull common factor an exponential of t squared, and actually okay, let's do it in 2 steps. This implies that our function y of t is -3/2 exponential t squared plus 1/2 exponential t squared times exponential 2t. And you see now I can pull common factor this factor and the 1/2 outside, which is what I was trying to do here. And then they are going to be common factor of what? Of exponential 2t minus 3. And there it is. That is our solution. This is how we solve a linear equation. Just by doing that. Now we are at our last problem, which is use the Euler method to find the solution of approximate solution of this equation. So solution Euler method. Euler method. Okay, what is that? So we want to find an approximate solution of an equation of the form y prime equal f of ty, and now notice that we have a t on the right hand side. Actually, it's a linear equation. We could solve it exactly if we wanted, but we are going to do it this way. And I think the problem said something like, let's write it down here, that we need to use the Euler method with delta t equal 1 on the interval 0, 3. We need this data to solve the problem. So this is our differential equation. Recall what is the main formula for the Euler method. If you don't remember the formula, it's not a big problem. What we need to do here, recall, is approximate f at some points, some partition n, yn, and then approximate the derivative by n plus 1 minus yn divided the n plus 1 minus tn, which is delta t. And from here you get the formula for the Euler method. Multiply by delta t and compute yn plus 1, and this is going to be we can write it down as yn plus f of tn yn times delta t. So the next element is the previous one plus something here. And where do we start? We start at the initial condition. The initial condition is going to give us that y0 is going to be 1 and t0 is going to be 0. These are our first element in the iteration for the Euler method. And let's start constructing a table here. Tn and here yn. It doesn't say how many. We are going to do 3 steps just to have an idea how this goes. So we start with n equals 0, which is 0 and 1. And now we need to go to n equal 1. So what is going to be y1? Well, y1 is going to be y0 plus f at t0 y0 delta t. But recall, delta t is 1. And now what is f at the t0 y0? Well, f, I didn't write it anywhere, but not well done. This is f. So this what we have here is f at ty. So let's write it down somewhere. So it's actually, that would be actually a good idea. So somewhere here we should write that f of ty is nothing more than t times y plus t squared. Okay, so when we say we need to evaluate f on these points, we mean at 0. So what we need to do is y1 is going to be 1 plus f at 0, 1. What is that? Multiply by 1, delta t. So this is 1 plus, and now we put f here. F is going to be 0 times 1 plus 0 square multiplied by 1. So obviously 0, and obviously this is 1, so y1 is 1. And recall now that t1 is t0 plus delta t, so it's 0 plus 1, so t1 now is 1. So here we have 1 and 1. So the yn didn't change when we move from y0 to y1. Okay, let's do y2. What is y2? y2 is going to be y1 plus f at t1 y1 delta t. So now let's replace. y1 is 1 plus f is t, so t1 times y1 plus t1 square delta t. Let's don't replace yet. Okay, now let's replace, and we have 1 here plus t1 is 1, so it's 1 multiplied by 1 plus 1 square times delta t, which is 1. So we end up with 1 plus 1 plus 1 is 3. Okay, y2 is 3. Nothing we can do about it. What is t2? t2 is t1 plus delta t, but t1 was 1 and delta t is 1, so this is 2. So t2 is 2. And now we have n equal to, we got that t2 is 2, of course, and y2 is 3. Cool. Last one. So you see more or less how it goes. What is y3? y3 is y2 plus f in t2 y2 times delta t. And recall that what is f? We have here y2. F is t2 multiplied by y2 plus t2 square multiplied by t. I'm just using this formula here. This is the right hand side of the equation. Alright, and now we replace everything, and what do we get? y2 is 3 plus, and now we have, this is 2 multiplied by 3 plus 2 square multiplied by 1. So what do we have? We have 3 plus, and now we have 2 per 6 plus 4. So we have multiplied by 1, so 10, so 13. And this is how more or less we build the interaction, and then we have t3, which is of course t2 plus delta t, which is 2 plus 1, which is of course 3. So t3 is equal 3. In our little, and we are going to finish here. And in our little table, we put here that n equal 3. So we have 3 here, and we got 13 over here. And that is the first 4 elements, so from 0 to 3 elements in the approximation, Euler approximation. So this is the Euler approximation for n equal 3. Depending how many you need to compute, well, that depends on the problem. I just cut it down to 3. So it's not too complicated, and this is a good place to stop. See you guys in the next video.